All right, good afternoon. How is everyone? Anyone here?
Doing well. How are you, Professor?
I'm doing well. How are the online lectures?
They're good.
Are we
Going,
making two?
yeah.
Any issues putting them up on YouTube? Is that easy enough for everybody to access?
Easily accessible.
Perfect. Can
And
you
the
guys watch
performance
me
of
at like 2x or 3x?
up to 2x, yeah.
I used to do this when I was a graduate student, so I assume that everybody else does this as well. All right, a couple of announcements, and then I want to do some examples today. First, I think that we've all been using Piazza a lot. It's getting a lot of posts, which is wonderful to see. The TAs are doing an absolutely spectacular job answering questions. However, I would like you guys to make sure a couple of things. One, make sure that before you post, you look to see if somebody else has already posted. Looking through there, oftentimes the TAs have answered that question, which is exactly why we like to use Piazza, so that everybody gets to see that question and everybody can get it answered. Two, the private posts, I'd like to minimize the private posts. A lot of people have been asking private questions when they're not really private questions. They really are general questions that the rest of the class would be interested in. So we'll start to make private posts public unless there's really truly private information in them. You should also just kind of remember that as you're posting your questions. Three, there's been a lot of questions on Piazza, often of the private form of, is this the right answer? Or, is this the right answer divided by 2? Or other kind of forms of answer checking. In general, that's not what we want to use Piazza for, and we will stop answering those questions. There were a few this time related mostly to cadence, and I think that those are appropriate only because I want to make sure that you guys learn cadence and we don't have issues there. But remember in general that we won't answer kind of, is this the right answer for the homework? I do encourage you to work with colleagues. So if you have friends that are in the class or want to meet some of the other students and work on the homework as a group, that's perfectly okay. You still need to submit your own, but that's a good way to kind of check your answers with another student. The TAs, they're doing an absolutely amazing job. At the end of the quarter, I told you guys I usually shoot to have the turnaround time at about 15 minutes. The TAs are off to an awesome start. They're answering, the average time to a lot of questions is under 8 minutes. It was at 7 minutes this morning. So that's pretty amazing when you think about the availability that you have to the TAs and how quickly they're responding to a lot of these questions. So the only thing I'll say is make sure that you appreciate them and make sure that you tell them how much you like the availability, and don't post kind of answer checking questions. There were a lot of questions about cadence on Piazza this week. Not untypical given that I realize that this is the first time that a lot of you are using Cadence. It's new software. Obviously, there's issues for all of us in getting access to this remotely. Just remember that the office hours are maybe a better way to get help on a lot of cadence related issues. Posting on Piazza, there's only so much that the TAs and I can see based on what you post. Whereas if you're in office hours, odds are the TA can just screen share with you, and in a matter of minutes, they will point you in the right direction of how to get your issue resolved. At this point, does everybody have access to Cadence, i.e. you've turned in your NDA and know how to get on the servers? Is there anybody that does not know how to do that at this point? Okay. Are there any issues with Cadence? Is anybody not able to do parts of the homework due to Cadence related problems that they're still having? Okay. All right, so that brings me then to discussing about homework. So how was homework 1? What was the general feel of it?
I found it a bit difficult.
Okay. Was it just difficult or was it long?
I think for me personally, it was, I mean, one, trying to just kind of get used to actually a real electronics class as opposed to my home university. But I think I found difficulty understanding sometimes what they were asking for. So I think like on, like some of the two that I still haven't finished was, or were able to complete was 6C through E. And like kind of figuring out how to manipulate kind of like a combination of that basic circuits knowledge with, kind of manipulating cadence.
Okay.
But it could just be new for me. I might just have to get in the swing of electronics again. So
Fair enough. I will say that, the midterm and the final will seem like very far away, especially if you're not used to the quarter system. The style of the homework problems and the style of the midterm and exam problems, they're all similar. Obviously in the midterm and the final, I won't ask A through G, but I often do ask A through C. And so stylistically, you can expect similar types of questions. So if there are issues in understanding what is really being asked, try to clarify those as soon as possible so that we don't have any issues there. Because I don't want issues in not understanding what you're supposed to do or what I want you to do. All right. I will say a couple of things about the homework. Homework 1, I think, should have been a lot of review for most of you. Obviously, everybody comes from different home institutions, whether you were at UCSD previously or another graduate school, an undergraduate. And so it is a little different, and I realize that. Be warned, I guess, that the homeworks will get a little bit more difficult. Homework 2, which I'll talk about in just a minute, I think is conceptually more difficult than homework 1, although probably shorter in terms of duration. Homework 1 was probably longer and just kind of more plug and chug rather than conceptually difficult, which they'll start to get a little bit more difficult in that regard. The other thing, homework is due at 5 today on Canvas. And just a quick reminder that there's no late homework. We will drop your lowest homework score. So if you are unable to turn it in or unable to turn all of it in, I would strongly suggest turning in what you can and getting those points. And then, if that ends up being your lowest score, we can drop that at the end. And then, just a reminder, please start early on the homework. Some of the issues with cadence were not cropping up until last night or this morning based on Piazza. And it's a little bit too late to wait until the day that they're due to get some of these things taken care of. And then lastly, one final comment, a lot of comments today, and then I can actually do some examples and talk to you guys. The homework, when you guys turned it in, I flipped through some of the early submissions. There's a lot of great ones that looked really good. There's some that are really hard to read. Please try your best to make it easy on the grader, in terms of legible solutions. I don't want you to type them. So scanning them in is perfectly fine. Some software that the TAs recommended, Adobe Scan, CamScan, and Office Lint are all relatively good. Just make sure that when you look at this, look at your solution that you upload, that it's actually readable. And when I scanned through them, I would say 90% were, and then there were a handful that had, what normally would be an 8.5 inch by 11 screenshot on Cadence that was shrunk down to 3/4 inch by 3/4 inch. And so you could generally recognize that it was a plot, but there was no chance that you could actually read what was on that plot. So, if your homework is 40 pages, that's fine. We're not counting the number of pages. I'm more interested that we can read it and that we fairly are able to assess your progress on it. All right, with that said, let me share homework 2.
Professor, I think you had mentioned this prior too, but in terms of like homework and like partial credit, I'm assuming there's like partial credit for like the A, B's, and C's, and we get it back and we can like discuss and things like that. Do you post solutions?
I do. The solutions will actually, that's partly why I don't accept late homework. The solutions will be out in 49 minutes.
Okay, awesome. Thank you.
Mm-hmm. All right. All right, so homework 2 looks a lot like homework 1. Couple of things that we're going to do. Problem 1, so during the lecture, lecture 4 in particular, I derived this, this metric for a transistor. It's called the transit frequency, or FT. It's a figure of merit of how fast a transistor can be. And I told you the answer in the lecture. I didn't derive it. I didn't prove it. And so what I'm asking you to do in this problem is to show that derivation, to prove out what the transit frequency for a MOSFET is. And the answer is just listed here. It's up to you to kind of prove it. I will say for a lot of our PhD students in the class, you eventually will have to take what's called the qualifying exam. This is, I would say, a question that I see maybe 15 to 20% in the qualifying exam. You know, obviously it's a lot more difficult and scarier to do when you have 3 professors staring at you writing on the board, but this is really your chance to get to practice this and make sure that you do know how to do it. It's a rather straightforward derivation, but I think that it is useful. All right, then we're going to do, we're going to analyze this problem here. And so in class, we've talked a lot about common source amplifiers. That was in lecture 3. But what's new here is that we're going to add some source degeneration. So we're going to add some resistance in the source terminal down here. And we'll see a little bit later on in this course that this is a form of feedback. It's a form of what's called series feedback in the circuit, where it's sensing the output current and it's feeding back a voltage to the input. It's a little bit indirect in how it does that. I'll explain it in much better detail later on. But what we're asking you to do, or what I'm asking you to do, is to derive the gain of this amplifier. And again, you know, I'm giving you the answer and I'm just asking you to prove it. Then we're going to play around with where this body is connected. So several times in the course, we've talked about the body terminal and whether or not it can get tied to the source or it can get tied to ground, and the effects of the performance on that. Here, we're going to analyze this circuit in 2 different ways, one with the body tied to ground and the other with the body tied to the source. Then we're going to calculate the maximum resistance, i.e. to increase the gain, and we're going to derive the gain for each of these different conditions to get different bias currents. And then, you know, I mentioned earlier that this was a form of feedback. There's a name for it when it meets a certain condition. It's called strong feedback, and we're going to derive the gain of this circuit when we have this condition of strong feedback, namely when GM times R1 is much, much greater than 1. And the condition will become very obvious when you're doing this problem. You're essentially going to be able to relate this to 1, and so you'll be able to drop the +1 term in the expression. And then lastly, I'm asking you at the end to derive the output impedance. So we're looking back in from the output to find the impedance that you would see looking back in. And so the reason why this is so important is because oftentimes when we get into multi-stage amplifiers, or we start talking about the frequency response, we need to know what's called the source impedance of the previous amplifier. And the source impedance will be the output impedance of this. All right, and then problem 3. Problem 3, we're gonna have some fun with MOSFETs, where we're gonna put them into kind of different configurations. I'll talk in just a second about this particular configuration and what this is. And you know, you're asked to kind of determine what the what voltage range for DC voltage, that is capital VI, keeps all of these transistors in saturation, and what the corresponding output DC voltage is. And then we're going to do some small signal analysis of this. We're going to calculate some gains, and then we're going to try to size this circuit to achieve particular gains. All right, problem 4. Here we're looking at combinations of transistors. And so we're going to put M or N rather transistors in parallel, where I connect all of their sources, I connect all of their gates, and I connect all of their drains. And I want to turn this into one equivalent transistor. And so you're going to figure out mathematically how you can find the equivalent transistor. For the parallel case, I think it's pretty straightforward. For the series case, you need to do a little bit of induction or think about the device physics, and the answer is straightforward, but it takes a little bit to prove. So there is some math here that you need to do. My suggestion is that if you can't generalize it to the case of N transistors to start with, think of just the case of 2. And really think about the region of operation that these transistors can be in. You should be able to quickly rule out several different permutations, and then you're just going to have to work through kind of the remaining 2 and figure out how you can generalize them. All right, and the last problem, we're going to use cadence, and what we're going to do is, I guess I forgot to mention this maybe last time, but you are all employees of Triton Industries, and I happen to be your supervisor. And so one of the things that we're going to do is we're going to design some switches. So switches are very common in analog circuits. There's a whole class of circuits called switched capacitor circuits or discrete time circuits that are based on switches, and so they're pretty important. What we're going to do is we're going to look at the on resistance of a switch using an NMOS, and we're going to use cadence to kind of sweep around some voltages, and then we're going to redesign this with a PMOS, and then lastly we're going to combine an NMOS and a PMOS together to make a better switch. Yeah. All right, any questions about homework 2?
So just the lecture so far will be sufficient, or should we wait for the lecture coming up Sunday?
Yeah. All right. Great question, and thank you for reminding me. So there was a couple of questions of, do I have to look forward in the lectures in order to find out the material for this homework? In general, you shouldn't have to do that. Homework 1, the assumption is that you've taken previous circuit courses and that something like a small signal model is not really new. In a sense, me reviewing it was more to supplement it with all of the additional capacitors and all of the additional elements that you may not have seen in kind of your simple small signal model. But I do expect you guys to have taken a previous circuit course and have a lot of that knowledge. But your question, moving forward, will you have to look forward? I hope not, and I've asked the TAs very specifically to look at this when they're making the solutions for the homework. Other questions? All right, so this will be due next Wednesday at 5. I will say that I'm working with the grader right now to make sure that we have a good way that's effective at grading your homework and getting it back to you. And so I've asked him, especially on homework 1, to try to get homework 1 done by next Monday or Tuesday so that you have time to incorporate anything into your homework 2. And in addition to that, we may switch how we grade homework 2. This is a little bit of a learning experience for all of us. I think right now we're just using Canvas. We are exploring the option of using GradeScope or other tools that may make this a little bit easier on him. So I would say we're going to stick with me. We'll try it on homework 1. We're going to see how things go, but we may change it up a little bit. All right, I think there's a question. So one of the questions asked in chat, Do the solutions that we're going to post online include the cadence problems? Yes. So the solutions that the TAs make, they have all of the problems, they have all the cadence. They don't have the files per se for the cadence, but they have all the solutions and work through that. And I would suggest that even if you, for whatever reason, were not able to do homework 1 or couldn't get problems 5 or 6 that are cadence-based to work, I would not give up on them. I would continue to make sure that you use or that you know how to do those problems, because we're going to use cadence the entire quarter. And these kind of things are not going to go away. So it's in your best interest to make sure that you know how to use cadence. It's a powerful tool. We're going to use it on essentially every homework. Will have 1, sometimes 2 cadence problems, and your project will be fundamentally based in cadence. So make sure that you iron out any kind of issues with access or with using cadence early on. Any other questions?
Since cadence came in topic, just question of like not too in the mainstream of the course, but is there any chance that you can explain some of the parameters in the model of the cadence? Like there are files, right? nfed.scs and others.
There are.
Is it possible? And if it helps, if it does not help much, then it's okay. We can skip over it. If it,
Yeah, I can, and maybe next time would be a good time to remind me. I'll have to pull up some files. I typically don't put those in my 164 lecture notes, but I do have them. In general, if you ever open up the model files, you're going to see hundreds, and I'm not exaggerating. There are literally hundreds of parameters to describe the MOSFET. What we typically use in our square law model is something like what's called a level 2 model, which you can describe with about 12 parameters. But yes, I can describe what a lot of those parameters are. Any other questions? Otherwise, I'm going to do some examples. Or at least I'm going to try. We're going to see if this works. All right, do you guys see the whiteboard or not?
yep.
Yes.
All right. I've got I only asked because I have a very interesting setup here. I have my iPad connected to my MacBook on Zoom with my pencil, so it's a very convoluted setup. All right, so one of the things that we often see in analog circuit design is what's called a diode connected device. And so a diode connected device in particular refers to when we have the gate and we have the drain and they're tied together. And so this essentially means that VGD is equal to 0. I'm not going to go into why we would want to do this today, but suffice to say, we're going to see this many, many, many times throughout this quarter. And so I want to kind of give you a little bit of context of 1, how to deal with this, and 2, historically where this comes from. And so if we think for just a second on the historical front, if I was to do the same thing with a BJT, and I was to connect the base and the collector together, what does this look like from, if I was to look into this device here? What does this look like?
Resistor?
Kind of.
Just
I mean,
a
it is
diode.
actually a differential resistor.
Just a
But-
diode, right?
Yeah, this is equivalent to a PN junction. And so this is where it gets the name diode connected device. Okay. So even though our MOSFET does not look like this BJT, its name comes from the transistor equivalent of when we do the same connection on a BJT. All right, so now let's look at what this diode connected device looks like from a small signal perspective. Okay? And so what I'm going to do is I'm going to draw the small signal model. And now when we have this diode connected device, I'm essentially making a connection here between the gate and the drain of this device. All right, so what happens when I make a connection between the gate and the drain of this device? The current through this device, through this transconductor, is equal to GM times VGS. Okay? But VGS is also equal to GM times VDS, given that the gate and the drain are the exact same potential when I do this diode connection. And so what does this mean? If I was to now connect this to a voltage source, and I started to increase this voltage source, what happens? I'm going to get a current that is going to flow into this device, and the current is simply going to be 1 over GM. From a small signal perspective, a small signal current. And so what this diode connected device does is this has an impedance looking back into this device of 1 over GM. Okay. So let's talk for a second about GM. Let's level set here. What are typical ranges of GM? All right.
Like millisiemens, right?
Well, let's back up for just a second. So we remember that there's a lot of equations for GM. One of them is 2ID over VOV. What's a typical range of a current that you might use in an integrated circuit?
Micro to
Microamperes?
milliamps.
Yeah, I think I would expand it a little bit, but reasonable. So let's say nanoamps to milliamps, with microamps probably being the most kind of common number. All right, and what numbers here are we talking about in terms of VOV? Is this tens of volts, hundreds of volts?
Like single digit
Microvolts.
voltage. Like single digit voltage.
Yeah, so VOV is going to be typically hundreds of millivolts. All right. So when I talk about hundreds of millivolts and milliamps to call it microamps to nanoamps, this gives me kind of a range of GMs that I would expect to see, right? And so, you know, microsiemens to millisiemens are probably the most common. It would be very hard for me to get a Siemen. It's also not typically picosiemens or nanosiemens. I mean, nanosiemens are somewhat, but typical transconductance range is going to be in kind of microsiemens to millisiemens range. So what is this impedance? So Z out or R out, this is equal to 1 over GM. Is this a low impedance or a high impedance?
Hi.
So 1 over, let's call it 1 millisiemens. That's like 1 kilo ohm, right? What if I was to add the output impedance in parallel with this, R naught? So R naught is typically going to be on the order of 10 kilo ohms to 1 mega ohm. Okay, so obviously these are dependent on how we size the transistor, how we bias it, and all of these other factors. But this helps kind of put some boundaries on where we would expect things to be. Okay, so GM, we typically expect to be in the microsiemen to millisiemen range. Output impedance 10K to mega ohm. And so when we do this type of connection, when we do this diode connected device, this typically results in what we would consider a relatively low impedance. And I'm saying low because it's relative to R naught, where R naught would be 10 or 100 or more times larger than. All right, one important thing to remember, when I'm doing this impedance calculation here, I'm doing this all for a small signal, okay? And so by definition, there is some DC voltage at the gate of this device, which is in turn at the drain of this device. I'm looking at small perturbations around that larger signal bias voltage, okay? This is not that I'm sweeping VDS from 0 all the way up to 1 volt. In particular, this diode connected device, it can only be in 2 regions of operation. So think about this for a second. If I have VGD is equal to 0 volts, what region of operation can this device be in? Can I ever put some voltage at the drain that puts this device in cutoff?
Could you repeat the question?
Yeah, what voltage, I mean, what regions of operation can this device be in?
For
Is it
V
cutoff or saturation?
0?
So if I put 0 volts here, the device is in cutoff, right? I have not formed an inversion there. So certainly this device can be in cutoff.
Hmm.
Now, as I start to increase it, can it ever be in triode?
No,
Why can't it be in triode?
because VDS is always going to be greater than VGS minus VDH.
Right. So VDS is always going to be greater than VGS minus VT. And so this means that this device can only be in saturation and cutoff. It cannot be in triode.
We are not discussing subthreshold here, right? Or
No, forget about subthreshold. We're not going to talk about subthreshold for a while, with the exception of today, actually. Pending time, I will give an example on subthreshold.
Okay.
All right, any questions about this diode connected device? It's going to come up time and time again, and we'll see it. So I just wanted to kind of prep us, given that it's already going to be on homework 2. All right. The next question that I wanted to ask is that we derived a small signal model for a transistor that was operating in saturation. Is there such thing as a small signal model in triode?
Isn't it in triode just a model as a resistor?
Close. So let's try to calculate this for 1 second. What's the definition of GM?
2ID over VOV.
Transconductance.
I knew somebody was going to say that. That's the solution. What's the definition of GM? So remember, I have a curve that essentially shows me VGS versus ID. And it looks something like this. The way that we figured out the transconductance at this point was by differentiating this curve, right? By finding or linearizing this around this point. So I'll give you guys one more chance. What's the definition of GM?
The integral of like ID or VGS.
Not the integral, but close.
I mean the derivative. Sorry.
So partial derivative of ID with respect to VGS at the operating point, Q. All right. So what's the equation for ID for a MOSFET in triode?
Oh, half of Kn into W by L into VGS minus VATH to into VDS minus VDS square by 2
Yeah? All
into
right.
W by L.
I'm putting it in Kn,
Okay.
but yes. All right, so what is the derivative of this? If I want to differentiate this with respect to VGS, what happens to this? What happens to this second term?
Goes to
Goes
zero.
away.
It doesn't depend on VGS, right? So what happens to this first term? Better yet, what's the derivative of this?
Kn into VDS.
So the transconductance of a MOSFET in triode is simply K and VDS. Does everybody see how we got this?
Yep.
All right, now what if I wanted to plot Kn, or excuse me, plot GM as a function of VDS? What does this look like?
A straight
Straight
line
line.
passing through origin.
Okay, so this is when the device is in triode. What happens when it gets into saturation?
Independent almost.
It's constant. All right, does everybody see how we did this though? Any questions about this? Because I want to do another similar problem. But before we go there, I want to make sure that everybody understands how we did this problem.
So perhaps you mentioned this at the beginning. I think I'm following how you did it, but I think why? What is the why are we doing it? Is it how is it relating? What's the application of this?
Yeah, well, I mean, every time you ask somebody what GM is, they're
Mm-hmm.
they're conditioned to respond to ID over VOV,
Mm-hmm.
which
Mm-hmm.
is true for a MOSFET in
In saturation, I see.
saturation. And the
Okay.
idea of a small signal model applies to a lot of, I mean, it applies to networks of circuits. So
Okay.
the definition, if you go back to the true definition of transconductance from a two-port network theory, you would understand this ID over VGS. And that's
Okay.
all we're trying to go back to here. And the next problem will make this a lot clearer. So let me show you the next one.
Okay.
I've got to juggle things here. Let's see if I can do this. All right. So this was a exam problem from, I guess, a while ago, 5 years ago. And the idea is deriving a small signal model for a field effect transistor, a MOSFET, operating in subthreshold. And I tell you that it looks a lot like a bipolar transistor. And I give you the IDS. So I give you the expression that governs its drain to source current as a function of VGS, the threshold voltage, VDS, lambda, and VDS. Okay? And I tell you I naught is the saturation current, N is the capacitive divider ratio we talked about, VTH is the thermal voltage, or 25 millivolts at room temperature. All right, so the first question that we're asked to do is to derive an expression for the transconductance of this device. And we can simplify our answer by assuming that VDS is greater than 4 VTH, such that the second exponential term is 0. So this is very nice. I'm being a really nice guy, and I'm letting us essentially, oops. Sorry, I meant to move this. Hold on. Not annotate. Oh my God, the disaster. Zoom problems. Okay, I'm back. All right, so this VDS being greater than 4 VTH, maybe thought I was back. This term. This says that the second exponential term is essentially 0. And the reason being that we essentially have e to the minus 4 here, such that this term goes to 0. And when we're doing the transconductance, when we're doing ID, we're often leaving the channel length modulation term out. All right, so how do we do part A of this problem? Help me out.
Just proceed the same way we just did, like
Yep.
differential.
Nothing fancy, right? So the exam problems will probably take this type of behavior. You're going to apply something you've learned to a problem that you have not seen before. They're not difficult. They're conceptually rather straightforward, but we are going to try to apply these techniques. So we know the GM, partial of ID, with respect to the input voltage, in this case VGS, around our operating point, which means that we're taking the partial derivative of I naught e to the VGS divided by NVTH. All right, what is this? What do I get when I take the derivative of an exponential?
ID by n phi t.
Yep. All right, so I get ID by N VTH. All right, any questions about how we did this part A? All right, so now let's read B then. So B is asking, derive an expression for the output impedance of this device. Note again, assume VDS is greater than 4 VTH. So here, it's saying that we can't neglect this term at the end, but we can still neglect that middle term. All right, so what is the output impedance? R naught is equal to what? What's the
Dou VDS
definition
by
of,
dou ID.
what's that?
Dou VDS by dou ID. Differential of VDS with respect to it.
DID, dVDS, 1 over that, right? All right, so in this particular problem, it means that we're going to have 1 over R naught is equal to times 1 plus lambda VDS. And so solving this, we're going to get that R naught is equal to 1 over lambda IDS. All right, any questions about this part of the problem? All right, so the part C says derive an expression for what's called the transconductance efficiency, GM over ID, for this device. So we're going to talk a lot about this later on in this course. It's a way of designing circuits is to use what's called the transconductor efficiency, or GM over ID. Here we simply need to calculate this. And we're going to do this for this BJT or MOSFET in saturation, and then we're going to do it for a MOSFET, and we're going to compare the two. So what we found that GM from part A was equal to IDS divided by N VTH. And so GM over ID is simply equal to 1 over N VTH. All right, so part D. Derive an expression for the GM over ID of a MOSFET operating in saturation. What's the transconductance of a MOSFET in saturation?
Two IDS by VOV.
Yeah, 2ID over VOV. And so GM over ID is 2 over VOV. All right. And so the last part is that assuming N is equal to 1.5 and VOV is equal to 200 millivolts, which of these devices has higher efficiency? So if we were to plug in numbers and we said that for a BJT, or for this sub-threshold, GM over ID was equal to 1 over 1.5 times 25 millivolts. And GM over ID was equal to 2 over 200 millivolts. This one gives us 26, 1 over volts as the units. And this one gives us 10, 1 over volts. So, which of these two devices has higher efficiency? The BJT. BJTs are always better. In fact, we'll show that you can never do as good as a BJT in terms of its transconductance efficiency. And so very quickly, why is this a good metric? Well, we're going to see many times when we're designing circuits, we want GM. GM is something that we need. When we were designing our amplifier, our very simple common source amplifier, the gain was GM times the output impedance. And so if we wanted more gain, we essentially needed more GM. And what do we have to pay, or what's the price for GM? We have to give it current. And so that's where this metric of GM over ID, that's why it's called the transconductor efficiency. How much do I have to pay to get the transconductance that I want? And what these two equations show us is that BJTs are more efficient than MOSFETs. And this is true. So this is why hardcore analog designers will always take BJTs. BJTs are better in almost every regard. But we're stuck with these MOSFETs as the digital people. All right, any questions about the example that I did today or lecture? Do you guys like the format of doing the examples?
Yeah, definitely. They're super helpful.
All right, good. All right, well, until next week, I'll see you guys. Enjoy the weekend, and I hope that you guys get an early start on the homework. Bye.
Thank you. Bye.